This one sort of gels, and that starts around -35, and it becomes more solid. And at about -60, it starts to have these expansive properties, or expansive forces. But up in this whole range, -35 to -60, it's sort of safe, but not really liquid. Problems with the antifreeze solution is it doesn't hold much heat, or it's not as easy to pump when you compare it to water itself. On the other end of the scale, when you boil water at about 100 degrees Celsius, that requires even more energy. To boil that kilogram of water takes 361 watt-hours. So I was saying down here that if I took a block of ice at -168 degrees Celsius, 1 kilogram of ice, and I heat it up to 0, I melt it, I heat it up to 99 degrees Celsius, that whole process takes the same amount of energy as it does to take it from that 99 degrees Celsius and turn it into steam. So steam contains a relatively large amount of energy. In our solar field, that's not really, it doesn't come up. We don't deal with steam in the work we're doing. But in energy efficient homes and systems, you've probably heard of condensing boilers and condensing systems. And so what they do is they avoid ejecting steam into the environment, and they eject liquid water, so that that extra 361 watt-hours per kilogram stays inside your home or whatever you're heating. The problem that we run into with steam is that 1 liter of water at atmospheric pressure, when it turns to steam, becomes 1,600 times the volume. And so if it's not confined to atmospheric pressure, if it's in a confined space instead of allowed to be at atmospheric pressure, then I just picked a random point at 330 or at 220 degrees Celsius. It will exert 300 psi, which is enough to be disruptive to our systems. So we need to avoid freezing because of the extreme pressure. We need to avoid steam because of the problems there. So in order to avoid steam, we put expansion tanks in our system, which allow the changes. I didn't really mention it, but the water will change the volume in its normal heat range. But also to avoid, if some of our water becomes steam in our collector, it can be absorbed in the expansion tank. And then we also have a pressure release valve on all systems that have even the potential of producing steam. In general, if all else is equal, including the volumes or masses, hotter objects contain more heat than cooler objects. But other than that sort of very contained example, sort of all bets are off. And I've restated some of the facts and figures I gave on the other page. But the same way that how tall something is doesn't tell you its mass, how hot something is in terms of temperature doesn't tell you how much energy is in it. And then another interesting fact I found was that in order to raise a liter of water, which is a kilogram of water, we need 1.1 watt-hours. To raise a kilogram of air, which is 833 liters, we need only 0.228 watt-hours. So in terms of heating air, we can heat more air to a different temperature with a smaller amount of heat. On the converse, it means that water is a better transport mechanism for heat than air is. And that's why a lot of high-efficiency homes use hydronic heating instead of forced air heating. And the final thing I wanted to talk about before I go into the system in this house is solar radiation. So how does the heat from the sun end up in our collectors? As a general rule, almost anywhere on Earth, if you have a square meter perpendicular to the sun, under full sun, the sun will transfer 1 kilowatt of energy to that square meter. 1,000 watts of energy strike a square meter during full sun, if it's perpendicular. So then, in order to find out how much energy you can expect on a solar collector or through a passive home, you need to know how many hours of that direct sun can you expect to receive each day. And these numbers are fairly well studied. This chart, the data comes from RetScreen, which is some free software available, sponsored through Natural Resources Canada. I have a few different orientations that are of interest. Tracking means if I follow the sun through the sky and I'm always perpendicular, my square meter is always perpendicular to the sun, this is the equivalent number of hours of full sunshine I'll get. Or, looked at another way, this is the number of kilowatts hours of energy I can get from the sun for a square meter on each of these days for each month. Then 90 degrees would be a wall mount collector, which is what we have on this house. 52 degrees is what the latitude of Saskatoon is. In some cases, that's an optimum angle for solar thermal collection. 20 degrees is what most of our installs are in the ballpark of, because most of our installs are on a sloped roof. And 20 degree west facing is for people who want a solar collector on their roof and they don't have a south-facing roof. And so you can see the difference in energy collection. One thing to note is the 90 degree one has a lot better wintertime collection. Another thing about the 90 degree or the south-facing wall install is the numbers are relatively flat. It's a relatively flat curve. The summer isn't much lower than the winter values. It's fairly flat line. So once you know how much sun can shine onto a given area, and we know how much energy is in the sun, the other factor that affects how much energy hits your collector is how much shading or what localized blockages exist between your collector and the sun. This top one is my house and the bottom one is Phil's house. In general, I have pretty good, especially if I'm just doing solar water heating, I have pretty good solar exposure. And Phil's is much more obstructed than mine. But even my house, each of these arcs corresponds to a month in the year, and each tangential line is an hour during the day. And so you can see the bottom three lines are November, December, January. November, December, January. And so those are probably the months that we're most concerned with space heating. And you'll see in mine, I have early morning blockages. I have maybe an hour. And then I have midday where the sun is most intense and direct blockages by these trees across the street. And this is up on my roof. So down on my wall, you can think lowering the whole curve, and I get even more shading effects. And unfortunately, that's typical of homes in the city. The Verico house is really lucky how it's located here. It has really good southern exposure. Any questions on any of that? So that's the background.
Has anybody been using water in collectors and just draining it back at night successfully?
So who's doing that, Phil? That John Segan-Taylor, who's one of the guys out of the States. Have you heard of him? He's really keen on that system. Everyone I've talked to a few people who really like that idea, and some people who are doing it. But everyone I've talked to, I've asked them if they've had systems fail, and they all have. They always have an excuse for it. Like it's the person who installed it didn't install it right is usually what I hear. But the fact is they've had failures, which is they're so expensive to repair.
Yeah, it requires everything to be able to drain back, so it has to be installed really well. That shouldn't be an excuse. Any plumber knows how to angle a pipe so it drains well, but there's a challenge in retrofitting in an existing house to get something to do that.
WSE has done some of those systems, but even theirs, they have everything sloped back, and they were still having ice buildup. And they cut the line to see the ice build up, and it built up in crescent moons, suggesting that it froze gradually over time, and they weren't sure where this moisture was coming from to build up. It would drain back properly initially, but then build up ice and block the lines.